In this video series, we've described the mesoscale convective systems that TropSat is designed to measure, how rapidly they evolve through their own life cycle, and how they serve as building blocks that scale upward to impact global weather and climate. We've detailed how sporadically those processes are covered by currently available sensor systems and how that sampling deficiency limits the understanding of the physics that drive them. One important impact of that limited physical understanding is a constraint on the predictive accuracy of current generation Earth systems and global climate models. Incomplete data access reduces time horizons for which they provide solid probabilities. In this video, we'll describe how the TropSat mission addresses this data deficiency in a low-risk, high-value manner that will contribute significantly to improving these critical predictive tools. We'll start with sampling frequency. Recall the animation that concluded the just previous video in this series. It illustrated the limited coverage by current spaceborne data sources of a large-scale, rapidly evolving convective event in the South China Sea. For a comparison, we'll again animate the 24 hours around that event, including all existing scatterometer passes, but this time we'll add the coverage that would result from TropSat. TropSat's swath will be approximately 1,800 kilometers wide, and it will never leave the tropics. Its precise orbit is one of the system's technical details that's still being optimized. That optimization looks for maximum coverage of tropical convective activity and employs analysis like this. The plot shows mean rainfall intensity by latitude for a 42-day period surrounding the active MJO in which our South China Sea event was embedded. That occurred during the December solstice, which leads to the southerly skew. The graph shows a fall-off in rainfall at about 20 degrees in the southern hemisphere. Because of the time of year, that same drop-off is sharper and occurs at lower latitude in the north. The dip at the equator is a known and expected feature of tropical convection, and the reason TropSat will not simply fly at 0 degrees. Using this analysis, we construct an example TropSat swath that extends to plus and minus 20 degrees in latitude. TropSat orbits will take 100 minutes, yielding 14 passes per day. As we start the same 24-hour animation, the TropSat swath gradually precesses westward. The South China Sea study area is highlighted with a red box when it's overflown by TropSat. Just after daybreak, you'll see the single pass by each of the two scatterometers that were operating at the time, ASCAT and RapidScat. What you'll also note is that as the TropSat swath moves into the study area, it generates a sequence of 8 consecutive passes over the event, capturing the precursor stages of its development and up through the multiple outbreaks of intense rainfall activity during its mature phase. This mode of burst sampling for large-scale convective events is a true game changer. We've described how quickly these weather systems develop. TropSat's low-inclination orbit and the rapid-fire sampling sequences it generates captures important aspects of their dynamic and thermodynamic evolution in a way that previously has not been possible. This unique orbital geometry addresses the data deficiency we've identified in space and time. But we also described a deficiency by type. That's the issue of what measurements are actually available. To address that, we need to look at TropSat's instrument package. As we've mentioned, the TropSat instruments are all in known categories with reliable track records and well-established processing paths. They include both active and passive sensors. Active sensors broadcast a signal and receive its return. These are radars. Passive sensors just receive emitted radiation from the Earth in a particular frequency that's associated with some physical property. Scatterometers are in the active category. TropSat will have scatterometers running at 2 different frequencies or wavelengths. The 2 wavelengths respond to differences in wind-driven ocean surface roughness in different ways. Comparing the 2 readings will allow for more accurate measurement of wind at different speeds. In addition, longer wavelengths suffer less from rain contamination. Sampling the same conditions at the same instant at 2 frequencies will allow better resolution of rain rate. It will also enable innovative new processing opportunities, potentially generating details like raindrop size. Recall that raindrop size is a differentiator between squall line and stratiform areas in an active MCS. Radiometers are the passive instruments. TropSat will have up to 3 of those. They measure sea surface temperature and generate layered readings of temperature and moisture up into the atmosphere. Finally, a microbolometer will observe outgoing long-wave radiation at the top of the atmosphere. A critical consideration in any spaceborne sensor system is risk. NASA assigns a designation of Technical Readiness Levels, or TRLs, to all mission aspects to quantify technological risk. Because of their long heritage, TropSat's instruments all score high TRL ratings. Only the integration of those instruments carries significant risk. The mass, size, and power requirements of the TropSat system are all those of a moderate-scale orbiter, roughly the size of a washing machine, and therefore compatible with a variety of new and increasingly reliable launch options emerging from the private sector. This opens the door to substantial reductions in cost. Again, because of the individual instrument system heritage, signal retrievals, error models, and accurate estimates of measurement precision are all in hand for a future TropSat data stream. Thank you for watching this video on TropSat technical specifications and how they impact the data sampling deficiencies we've identified for advancing the study of tropical mesoscale convective systems. Those deficiencies were in space, time, and by type. The TropSat mission has been specifically designed to address all three. In the concluding video, we'll cover the benefits that will accrue to both science and society as those new datasets emerge.